Folks, how's it going? It's Mr. Murray coming to you with a video on the Desmos modeling activity. So I'm putting this video together because I really am hoping that we can all work towards getting this activity done. This is a really important concept because this year has been all about studying different types of functions. So we started with linear functions. We then talked about, piecewise and absolute value functions. We talked about quadratic functions. And then most recently, we talked about exponential functions. Right? Throughout high school, you're going to study a whole bunch of other ones. And so what these are doing, though, is one thing they're doing is they're putting different tools into your tool belt that you can use to help model situations and kind of help make predictions about the future, right? That's one really important problem, right? That it's difficult to solve. We can't see the future. But by using data and trying to come up with a function that represents that data really well, we can try to make some forecasts that will help us make decisions. And so if you can come up with really, really good mathematical models, there's a lot of stuff that you can do that will, go a long way for you. Okay? So to get started in this first page, all you're going to basically do is just tell me where you're at, right? And there's no wrong answer to this. I just want to try to get a sense of how you're feeling because I want to close out the year on a good note and I want to give you the tools to be successful next year. Depending on how things go, I'd like to do a regression unit next year. I have a really fun activity about using a regression functions to make a roller coaster. And if you guys could work with me to understand how Desmos works, I think you would have a lot of fun doing that project. Okay. So in this slide, basically, all I'm doing is laying the groundwork for what we're going to be doing here. So regression is the process of creating a function to model data. How exactly regression function is found depends on the type of function you're looking for, right? So there's different processes essentially for finding different types of functions. So the types of functions we're going to look at today are linear functions, quadratic functions, and exponential functions, right? And in a linear regression, you're going to be finding a linear function like linreg found us in mx plus b. Quadratic regression is going to find us a quadratic function. And exponential regression is going to find us an exponential function. Okay. Now, ordinarily, if we were in school, right, I would talk to you about how to use the TI graphing calculator to do linreg, quadrag, and xreg. Unfortunately, right, that's not something that's available to everyone. I encourage you to investigate this on your graphing calculator. And in the Google Doc, I believe I put some notes on how to do that. So essentially, with regard to regression, we need to be able to do three things. One, given a set of data, we need to be able to find the three types of regression functions. And for that matter, you need to be able to, if I give you a table of data, explain to me how to put it in and find and write any type of regression function. Okay, but right now we're going to focus on linear, quadratic, and exponential. Now, the next thing you need to do is, based on your analysis of the graph and certain statistical values, you need to determine which of the functions is best at representing the data. So if we look at this function here, as seen in the graph, a linear function is not going to do as well as a quadratic function at representing this data. I know that because the points are closer to the parabola than they are to the line. So that's what I'm talking about, because the thing is, if we want to make predictions about the future, the best model, that is the model where the points are closest to the graph, is going to give us the best predictions, right? So in this case, the parabola is going to be more likely to give us realistic predictions than the line. Again, we don't know the context, but based on just the graph alone, we could maybe draw that conclusion. Okay, so again, find the functions, determine the best one, use the best one to make predictions. Okay, folks, so one thing that Desmos is really, really good at is helping us do regression. And so one thing that I hinted at earlier on in this video is that one thing we're going to likely investigate in course 2, honors, or CP, I think both of them do it, is regression, where we're going to use different types of polynomials, when we learn more about those, to model data. So Desmos is really, really powerful for doing this. And if we end up doing this really fun roller coaster project, it's going to come in handy. So to do regression, here's what you need to know. First, you need to make a new table. To do that, you're going to hit the plus button that's right above the very top on the left. It should be like somewhere up here, and hit table. Then you're going to put your x's in x1 or on your TI in L1 and your y's right here under y1 or in your TI calculator in L2. Now, this is how you actually go ahead and do out the regression functions. You can see here that we have linear, quadratic, and exponential. They look just like the general forms: y equals mx plus b, y equals ax squared plus bx plus c, and y equals a times b to the x. Now, the main difference here is that instead of saying x, I said x1, and instead of saying y, I said y1, and instead of using an equal, I use this tilde, which is found by hitting shift and the button to the left of 1. The tilde tells Desmos that you want to do regression. It's saying use this model to represent the data. Okay? So use this model, the linear one. And so when you indicate ax to the 1, what it does is it uses this x1 data, just like the calculator uses L1, and this y1 data, just like your calculator would do L2. And what it will tell you is the a and the b value that you would use to write the linear function. The same can be done with quadratic and exponential. Okay, so here we are on slide number 4, and here all I want you to do is just play around with the points and see how the graph changes. Okay, so right now we have a bunch of points, and I don't know, my birthday is 9/15, so I'm gonna add 9/15. So I'll type 9 for x, 15 for y. And you notice that as I add that second point, the graph changes. Now, what if I want to choose a point that's more along the linear track? So I'm going to choose, and this is just a random choice, 15, 21. Notice how, but as I change it, the regression functions automatically update. I'll delete the 21 so you can see. Notice how we had the 1.28, right, these, and then as soon as I add the 21, right, things kind of update. This one not so much. This one a little bit more, okay? You can also see that there's a couple values here. R squared and R, and these ones use R squared. So sometimes people use R squared to measure correlation instead of R. And R squared always returns a positive number, because we know that whenever you square a number, you either get 0 or positive. So I suppose it could do a 0 as well. But r squared is always going to be a number between 0 and 1. And the closer r squared is to 1, the better that model represents the data. So when we're just doing linear and comparing linears, that's when it's okay to use r, because I might be asking you to compare different types of correlation. But what you need to know is that when I'm going to ask you to compare across different types of models, from linear to quadratic to exponential, that is when you're going to want to use the r squared. And if you think about it, that's the only measure that's in every single one, right? I couldn't use r because, look, there's no r for the green or the red. Okay, so all you're going to do is just play around with some points and watch the graph change. 30, 10. Whoa. Right? Now the linear's r value goes way, way, way down. Watch. It was 0.91. Now it goes all the way down to 0.21. So you can see now the points are way off the linear, but yet you can see this 0.84 is an indicator that, look at how close these points are to the red parabola, while again this small, very close to 0 value of 0.15 lines up with the fact that the points are generally very far from the green graph. Okay, so this is just about playing with the functions and seeing what happens. All right, so now that you have a model, as with the linear regression, your job is you need to take that model and you need to turn it into a function, okay? Because Desmos only tells you the values. It's your job to actually format it the correct way. So here's an example. Let's say I plug in this data. So I want a function that looks like y equals mx plus b. So I type it in just like this. What Desmos is going to do is Desmos gives me my a and my b values, and then I need to take those and turn them into the function. So you can see what I did here. Y equals 1.15x plus 1.99. See, I take the a and the b and I plug them in where they go in the equation, right? Desmos' job is to give us those estimate values. All we have to do is then plug them in to make the function. You can see I did a similar thing for the quadratic, right? I took the a and plugged it in where I see a, the b where I see b, and the c where I see c. Just remember, here you do, when you're writing it out, want to keep it as x and not x1. The x1 is just being used for the purposes of creating the model, right? So your final model, again, see how I did x? You want to leave it with x in there. Okay, so what you're going to do here is you're going to show me what the exponential function would look like by, again, looking at these a and b values, taking them, and replacing them with the a and b values in the equation. And then the y remains your y equals, and then instead of writing x1, you're going to write x. Note that you need to hold down shift and press 6, and then see, you can get the exponent. So for example, 2 times 3 times 2, shift 6 to the x. Okay, so in the next few slides, this is a series of pages where what I want you to do is essentially investigate how you can get data to be linear, quadratic, and exponential. Okay, so there's two things. One, there need to be 10 points or more. I'll take actually more if you want. And whatever type of function I specify, in this case linear, has to be the best representation of the data. In other words, for linear, the linear graph has to do best. You can base that on a combination of the r squared value, which one is closest to 1, as well as visually the points being closer to the line than they are to the exponential curve or the parabola. Okay? So right now you can see the parabola is doing a perfect job. So maybe I'll add 4, 8. Okay, now you can see that the parabola still does a slightly better job. So maybe I'll add 10, 12. Okay, you can immediately see that now the linear is swinging here at an r squared of 0.86. And that's just about the same as the quadratic. So then you can imagine, add just a few more points, and now the linear will be best. Again, you need a total of 10 points. Once you have that best function, what you're going to do is you're going to come back and you're going to write that in. So for me, I would write y equals 0.88x plus 3.28. That's what I would write here. So all you're doing is you're just taking that best function and you're writing it in, rounding to 2 decimal places where needed. This is just about experimenting, having fun, and thinking about what this kind of data would look like. Okay, again, no wrong answers as long as there's 10 points and the linear is best. Okay, so 8 and 9 and 10 and 11 are going to be the exact same idea, except 8 is asking you to do quadratic, and 9 being writing the function. 10 is asking you to do exponential, with 11 being writing that function. Once you've had the opportunity to play around with regression, what we're going to ask you to do is try to model in real life. So I've actually put together at least one set of real life data that I'm going to ask you to use a model to draw conclusions on. So I went to the town of Milton, and the town of Milton publishes data on the number of positive COVID-19 cases in Milton. So what I did is I used the daily data breakdowns that have been released publicly, and I made this table here where the X values are the days since March 16th, the first day that we closed officially, and or rather I guess didn't have school due to the closure, and the Y values being the number of positive and or presumptive positive cases, because they may not have been confirmed positive in the beginning. Okay, until we had time to get the positives in. So these are what we're going with for X's and Y's. So what we're going to do is, through Desmos, we're going to create our linear, quadratic, and exponential regression model. We're going to determine which one is best, and then we're going to make some predictions. Okay, so in this, all I'm going to ask you to do is I'm going to ask you to fill in the table. This sketch will do the rest for you. I recommend you actually come back to this part and use your phone to take a little picture of, or your computer to take a little picture of it, and then pull up that picture so that you have access to it, because I think you'll find that it will help you, because there's a number of data lines and you don't want to keep flipping back and forth. Okay, so as you fill it in, though, what's going to happen is the points will appear on the graph. Keep in mind that I've specially designed the X and Y values to be compatible with the table. But what you're going to notice is as we fill in points, like, I don't know, the second point was 6, 4, 9, 15. Okay, so 6, 4, 9, 15. As we fill in the table, you're going to see that the regression functions fill themselves in and update themselves, and the R squared updates itself as well. By the end, you should be able to tell whether the red, which is linear, blue, which is quadratic, or exponential, which is green, okay, is the best function. Once you have the best function, you're simply going to write here which function is the best. I think the model is the best, and then you're going to write its formula, y equals whatever. Now that you have the model, you're going to just simply use that to make a prediction. So what I want to know is that on June 23rd, in a couple weeks, it's going to be the last day of school, and it will have been 99 days since March 16th. Using the best model that you found and wrote down in this step here, where x is equal to, think about it, what would x be equal to for 99 days in? Plug in using a calculator. You don't have to have this, you don't have to do this in your head. You can use a calculator, you can use Desmos or anything, any kind of calculator. I want to know, according to your model, approximately how many total cases will there be? Please state your answer in context. So on June 23rd, 2020, my model predicts that there will be COVID-19 cases. I know this because, okay, that's the kind of thing I'm asking for there. And it just has to be supported by math, and it has to make sense based on your best model. Okay, finally, you're going to be doing some stuff here on your own. Okay, so basically, this is a situation where we have a little bit of a radioactive leak, and radioactive particles go into the air and begin to fall down in a process known as fallout. So this table tells us the number of days since the meltdown stopped and the percent of particles that are still in the air. We need to make a model so that we can communicate to citizens when it's safe to leave their homes. This is going to be entirely up to you to figure this out, the table and the regression. Things you want to know. To do Y1, you're going to hit Y. To do the 1 down low, you're going to hold down Shift and press the button in between 0 and plus. It has a dash on it. And see how it goes down? Then you press 1. To get out of it, you press the right arrow, and you can see that it returns to bigger font. To get that little squiggly line, you hold down Shift and press the button to the left of 1. You can also feel free to go back to a previous slide and copy and paste as well. The rest of this will proceed the same as with the COVID situation. Identify the best model and state an analysis question in context. This last slide is just notice a little bit different. Here, there's going to be a 1% threshold. Here, it's going to be a 0.25% threshold. So this should actually say analysis question 2, and I'll try to fix that in a second if I can. But the idea is you just want to use your model to figure out approximately when is the radioactive chemical percent, in other words, the Y value, going to be at 1% or under for the first time, so we know when to tell people to leave. And then we'll answer that again, but instead of 1%, 0.25. And again, I'm giving you Y values here. Okay, and I'm asking you for X. So this is going to require some estimation, and that is perfectly okay. All right, folks, so hopefully this gave you some information to help you. I encourage you to have this side by side as you do the activity, but this is really, really important for next year, so I hope we're all able to get this done. All right, folks, best of luck. Don't forget to love math, and remember, you can do it. Until next time, have a